Well, the recording in the classroom has failed, so I'm going to record this in my office. We're finishing out the section on reacting mixtures and combustion, and we need to finish out the adiabatic flame temperature, talk about absolute entropy in the context of absolute entropy and doing an entropy balance for reacting mixtures and combustion, the third law of thermodynamics. Here's an image of a combustion. This is probably a can of butane or other fuel, and right in here it will be a combustion reaction occurring where you have the air and fuel at typically 25 degrees C or standard conditions, 1 atm, coming into a combustion chamber, and then going out would be a flame. And so the reaction is occurring where there is no work and no heat transfer out of this control volume. And if we apply the first law of thermodynamics to that system, this term is zero, this term is zero. If all of the reactants come in at standard condition, 25 degrees C, then the change in enthalpies are zero, and so we're left with two terms. So the energy balance equation says that zero is equal to the standard enthalpy of combustion plus the sum over all the products, N times the enthalpy at the adiabatic flame temperature minus the enthalpy at 298 Kelvin. This term, the standard enthalpy of combustion, was a negative quantity, and we find that as the adiabatic flame temperature increases, the enthalpy at that exit temperature is going to be greater than the enthalpy at 298 Kelvin. Hence, this is a positive quantity multiplied by the stoichiometric coefficients. All this is positive. So when the adiabatic flame temperature is sufficiently high, then it zeroes out the energy balance equation, and that's how you calculate that adiabatic flame temperature. Let's go ahead and solve a problem. Calculate the adiabatic flame temperature for butane with 100% theoretical air. So that's how much air we have. The fuel is butane. Both the fuel and the air enter at 25 degrees C and 1 atm. What do we want to calculate? Adiabatic flame temperature. What symbol do we use for that? Ta sub F. So adiabatic flame temperature is what we were asked to calculate. So first get a balanced reaction equation with 100% theoretical air. So we'll start off with the fuel butane, C4H10, and we don't know how much oxygen and the amount of nitrogen that comes in with the air. We'll figure out that coefficient in a minute, but it's complete combustion, and the carbon in the hydrocarbon fuel goes to CO2, and then we see that there's 4 carbons on the left-hand side of the reaction equation, hence there has to be 4 carbons on the right-hand side. Similarly for hydrogen, the hydrogen in the fuel, there's 10 of them. There's no hydrogen in the air, so the 10 H's on the left go to 10 H's on the right, meaning that there's a 5 in front of the water. Then we balance the oxygen first by adding up. On the right-hand side, there seems to be 8 oxygen with the 4 CO2s, and there's 5 oxygen with the 5 H2Os, giving us 13 O's. Now we can come back and balance. 13 divided by 2 is the amount of the coefficient in front of the O2. We finish the reaction for the nitrogen. It'll be 13 divided by 2 times 3.76 N2s. And if you take a look and make the computation, this is 24.44. So for 1 kilomole of butane fuel, you'll have 24.44 moles or kilomoles of nitrogen going out in the flame. All right, so that's our balanced reaction equation. We go ahead and write our first law. 0 is equal to the standard enthalpy of combustion plus the sum over all the products, and we'll go ahead and expand this out so it's the stoichiometric coefficient of the product, the molar enthalpy at the exiting adiabatic flame temperature, and the molar enthalpy at the reference 298 Kelvin temperature. There. We have calculated the enthalpy of combustion for different fuels before. Remind you, it's the sum of the stoichiometric coefficient times the enthalpy of formation for each of the products minus the sum, the stoichiometric coefficient, enthalpy formation for each of the reactants. In this case, let's go ahead and write this out for the products. So what we're going to have is 4 enthalpy formation for the CO2, and then we're going to have plus 5 enthalpy of formation, the H2O, and that's going to go out in the vapor state. This adiabatic flame temperature is very high. It's not going to go out in the liquid state. And then we have subtracting the coefficient 1 in front of the butane fuel, then the enthalpy of formation for the C4H10 fuel, giving us a total, when you make that computation, of negative 2,657,030 kilojoules per kilomole. Note that the enthalpy of formation of the oxygen and the nitrogens are 0. All right. So now we take a look at expanding out our energy balance equation. So we have 0 equal to minus 2,657,030 kilojoules per kilomole plus the sum over all the products. So we're going to have 4 times the enthalpy at the outgoing adiabatic flame temperature minus the enthalpy at 298, all on a molar basis. I don't know why I put a bar over that temperature, get rid of it, for the CO2 plus 5 times the molar enthalpy at the adiabatic flame temperature minus the molar enthalpy at 298 for the H2O plus 24.44 molar enthalpy at adiabatic flame temperature minus molar enthalpy 298, all of that for the nitrogen. All right. So at this point, what you have to do is realize that this is basically a root finding. So you're looking to find an x such that the function f of x is equal to 0. And so what we see is over on the left-hand side of our equation, there's 0, 0. Our equation is a function of the adiabatic flame temperature. So what you can do is recall from your numerical methods class things like Newton-Raphson or bisection or secant method, a number of different techniques. But what you do is you have to start somewhere. So guess the adiabatic flame temperature. So I'm going to guess a temperature of 2000 Kelvin. And when we put a 2000 Kelvin right in here, right in there, and right in there, then we can evaluate everything on the right hand side of our equation. And when we evaluate everything on the right hand side of the equation, we calculate negative 555,739. So I had to go get the molar enthalpy of the carbon dioxide at 2000, the molar enthalpy of the water vapor at 2000 Kelvin, and the molar enthalpy of nitrogen at 2000. Let me show you the table right here. You would be using table A23, and you would need the carbon dioxide molar enthalpy at 2000 Kelvin. So there's a value that I need. Subtract off the value at 298 Kelvin. That's the delta H bar. Likewise for water vapor, you have the enthalpy at 2000 subtracted from the enthalpy at 298. And for nitrogen, the enthalpy at 2000 minus the enthalpy at 298. So those are the 6 values you take the difference of in order to evaluate the right-hand side. We see it's negative right here, indicating that we didn't guess high enough in the adiabatic flame temperature, because as the adiabatic flame temperature gets larger, that summation over the products is a greater positive value, and then it'll finally match the large negative enthalpy of combustion. And then if you continue to overestimate the adiabatic flame temperature, then it'll be the right-hand side will become positive and not negative. So at this point, you can guess 2,500. Do the same thing, and you'll come in with 141,679. So we've bracketed the solution somewhere in between. At this temperature right here, we don't know what temperature it crosses through. The right-hand side is equal to 0. Just do linear interpolation. So the way I think of it is the fraction of the distance from here to here versus here to here. So that's the interpolation fraction. So it'll be 0 minus a minus 555,739, 141,679 minus a minus 555,739, and that fraction comes in right at 79.69%. So 79.69% of the way from 2000 to 2500 is the next best estimate of the adiabatic flame temperature. So the adiabatic flame temperature comes in right at 2398 Kelvin. Well, you could double check it, but this is close to 2400 Kelvin. When you run the equation again, it's very near 0, and that's the answer. These systems are slightly nonlinear in the enthalpies as a function of temperature, but it won't take many iterations to hone in and get an estimate that's very accurate. So I'm going to just call it quits right there, that the adiabatic temperature is around 2400 Kelvin. You can go out to the literature and you can find where people have reported the adiabatic flame temperature for different fuels. First of all, you'll notice, let's say right here, the fuel of acetylene, used a lot in cutting torches. You can use it where the oxygen is coming from either air or pure oxygen. And notice that the adiabatic flame temperature, when it's coming from air, is lower than the adiabatic flame temperature if the oxygen was coming from pure oxygen. Why? Because there's no nitrogen that have to heat up in the products. If we go back and take a look, that's quite a few moles of nitrogen that have to be heated up from 298 to whatever the adiabatic flame temperature is. So the fuel that we just evaluated was butane. We combusted it with air, and we calculated 2,400 Kelvin, which is around 2,130 degrees C. So around 2,100, little over degrees C. If we look at the value reported, it's substantially less. So this is lower. And you say, why is it lower? Well, the predicted adiabatic flame temperatures are going to be higher than the reported experimentally measured values, because our model assumed that it was complete combustion, and often the combustion is incomplete. Or not often, like it's hugely incomplete, but there's enough unburnt fuel or partially burnt fuel that it's going to have a lower temperature because of that unburnt component. Also, in order to try to encourage complete combustion, often it's better to bring in a little excess air, and that will help more of the combustion to be completed. Also, we know that flames are hot. They are visible. You could see the color the orange and the blue, that's radiative heat transfer coming off of it, and so there's a little heat loss. It's not truly adiabatic. And also, this is very similar to incomplete combustion, that the carbon dioxide, if it's very, very hot, could dissociate back to some carbon monoxide, and that would be like ready to continue to combust. So dissociation of the water, maybe dissociation of some of the nitrogen, and dissociation of the carbon dioxide, those products. So you guys just take a look through this table. You can see that the regular pattern, that hydrogen with air versus oxygen, it's higher, it's lower. Down here is MAP gas, and you can purchase quite a few of these gases. Here's a little bottle of butane that you could purchase from one of the hardware stores. Here's a Lowe's, it's from the Lowe's, and you can fill this little lighter, and it has a little push button, and the flame would come out here. And so they have many uses in the garages for soldering, or also I heard in the preparation of food, they'll have a little a butane torch or another torch, and they'll top off the tops of pies or other desserts and caramelize the top with a little flame. Now that we've done the energy balance for reacting systems, we now need to move to entropy balance for entropy, or move to entropy balance for reacting systems. First of all, we're only going to handle steady state conditions, hence typically this side would have some transient component, but it's set to 0 for steady state. We follow the same type of form for entropy balance. You have entropy coming into the system with the heat transfer. This rate of heat transfer is coming into the control volume, and you have the boundary temperature at which it comes in. So that's a rate of entropy transfer with heat in. You have all of the reactants coming in, the molar flow rates and the molar entropy, and the products are all going out, the molar flow rate and the molar entropy. And if there was some irreversibilities, it would be a source of entropy or entropy generation inside the control volume. So I like to write this as an in, and in, and in, and this one is an out, and the out has a minus sign in front of it. The rest are plus. Alright, so that's our entropy balance equation. What we don't know is how to calculate the entropy, because when we have reacting systems, that's new. So we think back, what did we do when we wanted to calculate energy for reacting systems? We had a enthalpy of formation, which tied things together, which took into account the chemical makeup of all the substances. Well, you do the same thing for entropy. You tie it back to an absolute entropy, and the form of the absolute entropy is that it's a function of both the temperature and pressure. And a lot of times our products or reactants behave as ideal gases, so this form is for an ideal gas. And so you have the function of temperature only minus R bar, the universal gas constant, the natural log of, and then a function of pressure only. So you have the temperature and then the pressure side for evaluating the absolute entropy. Let's take a look here to see if we understand each of the terms. R bar, universal gas constant, P ref, 1 atm. It's our standard atmospheric pressure of 1 atm. This is our pressure of whatever that substance is at in the mixture. So if it's CO2 you're calculating the absolute entropy of, then it would be the pressure of the products times the mole fraction of that CO2 or whatever species or component you're looking at. And this is the absolute entropy at standard temperature and pressure, actually not standard temperature and pressure, standard pressure of 1 atm. And this takes into account the temperature. So now there's something called the third law of thermodynamics out there in the literature. And when you have the concept of absolute entropy introduced, the absolute entropy is set to a value of 0 at an absolute temperature of 0 for a pure crystalline substance. So this is the reference or the base or the datum point by which entropy calculations are made. So the S bar not equal to 0 is when the temperature is 0. Can you ever get that cold? No, but at 0 Kelvin, theoretically, you get that cold. And for a pure crystalline substance, what's the opposite of a crystalline substance? Is something that's non-crystalline, or what we might call amorphous, unstructured. So a crystalline substance is very structured. So harken back to our concept of entropy as a measure of molecular disorder of the substance. And so the entropy for a gas versus a liquid versus a solid. And when you have the entropy goes up because the molecular disorder of the system is increasing when it's a gas versus a liquid versus a solid. All right. Well, here you have not only a crystalline solid, but it's a very well organized solid. Hence, you have no or minimum uncertainty in or randomness of our molecules that are making up that substance. And so it's like all set up on a nice lattice system, and if the temperature is down at 0 Kelvin, then what we have is that the molecules that are at these lattice points, they wouldn't even be wiggling or have any motion. They would be rigid in location at 0 Kelvin. Hence they don't move. Hence everything is well defined in its location. There's no randomness, no disorder in it. Hence it has a 0 absolute entropy values. All right. A couple comments. It's impossible to get to absolute 0 entropy, but to use it for the calculation purposes. Let's take a look at our table, A25, and now we can understand more of this column over here for absolute entropy. And again, the symbol is S bar, meaning it's entropy per amount or per kilomole, and not meaning that it's at the 1 atm. Here they only give one value in the table, so it's the value at 298 Kelvin and 1 atm, standard temperature and pressure. Okay. Notice that you do have a solid formula, so this was carbon in the solid phase, and it has the lowest value of absolute entropy in the table. The next thing to notice is there is a liquid, H2O liquid, in this table, and it has an absolute entropy that's greater than the solid, but it's less than all of the other gases that we have. Look at the magnitude of the absolute entropy for the gases. They're higher. So that just confirms the notion that solids more organized, lower absolute entropy, gases less organized on a molecular level, highest entropy values. We can also compare the tables, let's say table A25 and table A26. So if we take a look at, excuse me, so if we take a look at the carbon dioxide, CO2, first of all, you notice that they repeat the value of the enthalpy of formation. The enthalpy of formation, negative 393, 520. If we come up the carbon dioxide, we find that values in both of those tables. And so those values are consistent. Also, we notice that the absolute entropy for carbon dioxide at 298 S bar naught right here for this column is consistent. So that's nice to see that those values are consistent. The same is true for the carbon monoxide. Here's the enthalpy of formation. Enthalpy of formation for the carbon monoxide absolute entropy at 298, absolute entropy at 298. Same for the water vapor. You have this value for the enthalpy of formation, same, and absolute entropy at 1 atm, 298 matches. So that's all good. And again, for the enthalpy of formation of the oxygen and its enthalpy at absolute entropy at 298. Let's solve another problem. We have a gaseous mixture of methane and oxygen at 298 and 1 atm. It enters a fuel cell operating at steady state. So we have a fuel cell, and we have already a gaseous mixture of CH4 and O2. It's not pure CH4 and a separate stream of pure O2. They're mixed coming in. And then what goes out? Streams of carbon dioxide go out. Now the carbon dioxide is going to be in the gaseous state, and liquid water exit. I'm going to put the liquid water, H2O, exiting clearly downward in its separate stream, and that's liquid. But both of them exit at 298 and 1 atm, so there's the same temperature of inlet and outlet. The fuel cell operates isothermally, so anywhere around the boundary it's 298 as well. Develop the maximum theoretical work that the fuel cell can develop in kilojoules per kilomole of methane. So what we're asked to calculate is W dot of the CV divided by N dot of the fuel. So won't that give us the units of kilojoules of work per kilomole of methane? I think so. And we're going to have a control volume around this fuel cell. For that control volume, we'll have the concept of W dot out of that control volume. And also we can have Q dot in for that control volume. There's nothing said about Q dot. It doesn't say it's an adiabatic fuel cell. It just says it's an isothermal, or it operates isothermally. All right. And we're interested in calculating the maximum theoretical work. Well, these are trigger words or key words indicating, if we want a maximum theoretical work, we probably want to look at the second law of thermodynamics, and we probably want to say something about no friction or no irreversibility. So entropy generation is 0, and that would then minimize or maximize work. In this case, it would maximize the work. So let's go ahead and write our balanced reaction equation. We have CH4 plus oxygens coming in, and we're going to create carbon dioxide gas going out. To balance the carbons, it's a 1 in front of the CO2. And then H2O, to balance the hydrogen, it's 2 H2Os. We count up, we have 2 oxygen, 4 oxygen. We're going to need 2 O2s, and that's our balanced reaction equation. So one thing that we're going to need to know is the mole fraction of the CH4 that comes in that reactant stream. Well, you have 1 mole of CH4 and 2 moles of oxygen, giving you a total of 3 moles of the reactants coming in. And for each 3 moles of the reactants, 1 will be the methane and 2 will be oxygen. So the mole fraction of methane in the reactants is 1 out of 3, and the mole fraction of oxygen in the reactants is 2 out of 3. So 1/3 and 2/3. Okay, good. Let's go ahead and write down then our second law for this reacting system. So our second law would read something like the sum of the molar flow rates times their absolute entropy for each of those reactants, that's all coming in, plus any irreversibilities that would create or produce entropy, that's an N, inside that control volume, plus Q dot coming into the control volume divided by the temperature of the boundary of the control volume, which is going to be 298 Kelvin, equal to the only out, the sum of the molar flow rates times the absolute entropy of all the products. So we can rearrange this second law and get an equation like this. Q dot into the control volume per N dot of the fuel is equal to the boundary temperature, TB, times the sum over all the products of the stoichiometric coefficient, S bar, minus the sum over all the reactants, stoichiometric coefficient, absolute entropy, minus sigma dot CV, close parent. Okay. If we also write the first law, energy balance for that reacting system, I'm going to write it like this: Q dot CV divided by N dot F minus W dot CV divided by N dot F equal to the sum over all the products, the stoichiometric coefficient, molar enthalpy, minus the sum over all the reactants, stoichiometric coefficient, molar enthalpy. And we substitute and eliminate, whoops, put it right there, the Q dot over N dot F, and then we can get one equation, I'll write it up here, that the power out of the control volume per molar flow rate of the fuel is equal to the sum of the stoichiometric coefficient times H bar minus the boundary temperature absolute entropy over all of the reactants minus the sum and H bar minus TB S bar over all of the products. You could write it a couple different ways, but that's just one way of writing it. And so what we can do is expand out now. If we sum over all of the reactants, let's just kind of write them down. The reactants are going to be CH4 and O2. Sum over all the products are going to be CO2 gas and H2O liquid. Emphasizing that's a liquid. All right, so what we're going to have is the stoichiometric coefficient for the fuel. Maybe I'll write it out like C times enthalpy formation plus delta H bar, that'll give us the enthalpy, minus TB times S bar naught at T minus R bar natural log of Y P over P ref. And I think I got that finished. All right, and all of that's for the CH4. Okay. Okay, so then we would have the same thing for the oxygen, the number of moles times enthalpy of formation plus the change in the enthalpy from the reference 298 to whatever the reactant's coming in at, minus TB S bar naught T minus R bar natural log of Y P over P ref, close paren, O2. And the same thing for the other two. Whoops, leave mine a minus sign. Then the number of moles times the enthalpy of formation of the carbon dioxide, change in enthalpy, whoops, minus TB S bar naught at T minus R bar natural log yp over p ref. Close, close, close. This is the CO2 minus. Now, that H2O liquid is coming out. Let me jump back to our equation for the absolute entropy. So if we take a look at the absolute entropy, this was for an ideal gas. What happens if it's incompressible? What happens if it's incompressible? Well, the molar entropy it's a function of temperature and pressure for that component, but it becomes a function of temperature only for that component. That's our standard approximation. Because it's incompressible, the pressure doesn't change the volume, hence the pressure can go up or down but not change the entropy. And you have just that, if you wanted a simple model, it would be something like the C sub P natural log of T divided by T ref or something like that. But the important point is that it's a function of temperature only. So when we come over here, and the next thing we're going to do is for the H2O liquid, all right, we'll start out, we'll have the stoichiometric coefficient, we'll have the enthalpy of formation, any deviation, minus TB, and then we're just going to have S bar naught at that temperature minus 0. Not, there's no this other part which is only for ideal gases. All right, there's a bunch of terms that are 0. First of all, everything's 298 in and out, so that's all 0. The next thing is the incoming pressure of the mixture is 1 atm and the reference pressure is 1 atm, so they cancel, leaving inside the natural log of the mole fraction for the CH4. That mole fraction for the CH4 was 1/3. Same thing, it cancels for the oxygen, but the mole fraction for the oxygen incoming is 2/3. All right, but take a look at what outgoing CO2 stream. It's pure CO2 going out in the gas. There's nothing else. So these P's they cancel. Both of them are 1 atm. And that Y is 100%. And the natural log of 100% is 0. All right. So that term is 0. Well, let's take a look at every one of these TBs is 298, right? 298, 298. We have to get the enthalpy of formation of our fuel. Enthalpy of formation of the methane, negative 74,850. The absolute entropy at 298 for methane is 195.29, and R bar we know 8.314. Let's take a look at everything then for the methane is known, except for I forgot to put the 1 for the stoichiometric coefficient. For the oxygen, 2 for the stoichiometric coefficient. The enthalpy of formation for oxygen, 0. Absolute entropy for the oxygen, this term right here would be like 208.4. Very good. We know the R bar and the natural log of the Y is 2/3. Okay, a Y of 2/3. Then we come down here for the CO2, the stoichiometric coefficient is 1. Enthalpy of formation, negative 393,520. And the absolute entropy, carbon dioxide at 298, 213.685. And then the coefficient for the water, 2. Enthalpy of formation liquid, water, negative 285,830. And the absolute entropy, 69.95. When we make that computation, we find that W dot CV divided by N dot fuel comes in at around 813,000, and I'll just round it off to there, kilojoules per kilomole. If you go back and take a look at not setting this term equal to 0, what will happen is if you do have some entropy generation, then it'll change Q dot, changes W dot. But this is set with sigma dot equal to 0, no irreversibilities. That would give our maximum theoretical work. All right, so the last thing I'd like to do is just summarize the 3 laws of thermodynamics, because this is the new one right down here, the 3rd law of thermodynamics. Well, what was the first law all about? The first law was about energy, and it said that energy can be realized in many different forms, but the sum of the energy is constant. So we had the notion that energy is conserved. That's the first law of thermodynamics. Oh, it can be transferred in and out of a control volume with heat transfer and work transfer. It can be changing forms between kinetic, potential, and internal energy, but that the sum of all of the energies is conserved, so it's constant. What about the second law of thermodynamics? Well, in review, we've studied the second law, and we found that it dealt with the direction of energy conversion. So some conversion of energy between forms is easy, some is hard, some is limited, some is unlimited. So the conversion between heat and work is limited. It's hard. You just can't convert 100% of the heat into work. But you can convert 100% of work to heat. That's easy, it's friction, and we often want to avoid that in real systems. So there is a second law is a statement on the limitation of the transformation of energy between forms, and you get the notion of some forms of energy are more valuable than others. What about this new 3rd law we just introduced to? Well, it says that a molecule or a substance has some molecular motion at a temperature above 0 Kelvin, but as you get colder and colder and colder, if you get down to 0 Kelvin, the molecules have no more motion, and in the context of having a crystalline structure, then there's no uncertainty in the motion or the location of molecules relative to each other. So the 3rd law deals with this concept of no molecular motion at absolute 0. Well, a long time ago, people thought of analogies for the conservation of energy, 1st law, 2nd law, 3rd law, and they thought about it in context of money and gambling. And so let me just share with you these thoughts. So for the 1st law, the analogy is energy is conserved, but for money and gambling, money is conserved. When you gamble, either you win and somebody else loses. Maybe you're playing in Las Vegas, you're playing at a casino, they call that the house. So either you win and the house loses, or the house wins and you lose. But at the end of the beginning of the night and at the end of the night, there's the same amount of money somewhere. It may have changed in location, but it's conserved. So that's the money and gambling analogy with the 1st law. With the 2nd law, there's a preferred direction to the transfer of energy or energy conversion. Likewise, in money and gambling, we know that there's the statement from the 2nd law that the house always wins. 1st law says the house could win or you could win, but the 2nd law says there's a preferred direction of winning. The house always wins. Now, what about the 3rd law? In energy, it said you have motion until you're at 0 Kelvin. And when you're at 0 Kelvin, you're absolute 0, you have no molecular motion. Well, in the context of money and gambling is you can't stop gambling until you're dead broke. So that's the joke, that these 3 laws of thermodynamics in the context of money and gambling.